Page 9 of properties of curves. We're going to continue on with the exercise we were doing on page 8. We're just going to take these three functions. We're going to find and classify their stationary points, and we're going to sketch each function. So the first one is a cubic. In order to find the stationary points, of course, we need to find the derivative. This is not a difficult derivative. It's just power rule, right? Go, and we're done. Derivative of 1 is 0, of course. So there's our derivative. I can simplify this into negative 12x, right? In order to find the stationary points, I need to set this equal to 0. A little bit easier if I factor out a 3, right? So it would be x squared minus 4x plus 4 equals 0. I can factor this into x minus 2 times x minus 2, right? So the two stationary points would be x equals 2 and x equals 2. So there's only one stationary point at x equals 2. Let's classify the stationary point. So if we draw a sign diagram for the derivative function, that is 0 at x equals 2, what is the sign of the derivative for a big positive number? Positive times positive, it will be positive. What is the derivative sign for a big negative number? Negative times negative is positive. So this function is increasing to the left of the stationary point, and it's increasing to the right of the stationary point. So it has a shape like that, which we know is an inflection point. So it's a stationary inflection point. Let's sketch it here. So I'm going to sketch it on this grid. And I'm going to sketch it in blue. And basically the shape is going to be centered at x equals 2. I can actually use this grid. So at x equals 2, it's going to be have its inflection point, and then it's going to continue going up. It's going to be momentary flat at the inflection point. I could figure out exactly what height it's going to be at by plugging in x equals 2 into the original function. If I do, it will be 2 cubed minus 6, 2 squared plus 12 times 2 plus 1. So that would be 8 minus 24, which would be like negative 16, plus 24, which would be 8 again, plus 1 equals 9. So the height of this function, inflection point, would be 9. What would be the y-intercept? The y-intercept would be 1, because if I plug x equals 0 in, the y-intercept would be 1. So the y-intercept is 1, the inflection point height is 9, and otherwise this is, I think, a fairly good sketch of E. Okay, let's look at G. So for G, this is also not too difficult of an integral, but in order to make it easier, let's rewrite radical x as x to the 1/2. Then it's a little easier to see that we just do power rule, and we get that, okay? And then if we want to know when our where our stationary points are, we set it equal to 0, and then we solve for x. So this would be, I'm going to rewrite it using the radical sign. So 1 minus 1/2 square root of x in the denominator equals 0. We can rearrange this a little bit by adding 1 over 2 square root of x to both sides, and then we'll get 1, 2 square root of x like that. And then we could cross multiply, and we'll have 2 square root of x equals 1. And then we could divide both sides by 2, and so we'll have square root of x equals 1/2. And then we could square both sides, and we'll find out that x is equal to 1/4. Okay, so our stationary point is at x equals 1/4. Let's draw a sketch of this. And let's see, if this is 1/4 here, then, oh, we didn't do our sign diagram yet. Let's do a sign diagram. So 1/4 is where there is a stationary point. To the right of 1/4, we will have let's see, if we put in a big number here on the bottom, it's going to make this fraction very small, and so it would be positive. Positive. If we put in a smaller number, and remember, some of these numbers we can't plug in because remember, square root of x, you can't put in an x value that is smaller than 0, right? So the smallest value we could put in would be 0. If we do plug in 0 into our derivative function, you can see that this becomes infinity. So that means that at 0, it's kind of an infinite slope, it's a vertical slope. In between 0 and 1/4, if I put a very small number in for x, I would get a number that would make this fraction a little bit bigger than 1, because like if I put, like, I don't know, 1/8 or something in here, the square root would 1/8 is kind of awkward, but if I put in like 0.1 here, the square root of 0.1 is about 0.3. 2 times 0.3 is 0.6. I would end up with a fraction that is slightly more than 1, so I would have a negative derivative for values in between 0 and 1/4. So I could put in my sign diagram that would be negative here. So basically, if I drew the shape, I would go down first until I hit 1/4, and then I would go up. Okay, and the position of this, I could position it by finding out what the y-intercept is. I find the y-intercept by plugging in 0 in here. 0 minus square root of 0 is 0. So it actually is going to start at the origin, and it's going to go down a little bit, and then it's going to go up. Okay, so there's my sketch for G. Okay, and finally, let's do F. So for F, I'm going to do it down here. I'm sorry, it's I. For I, we'll do it down here. And I has a function which is equal to 1 minus x to the 3/2. I rewrote this as x to the 3/2 is x to the first times x to the 1/2, x to the 3/2. I'm going to take the derivative so that I can find the stationary points. So the derivative would be, let's see, if I take the derivative of the first term, which is 1, that would be 0. And the derivative of the second term, which is x to the 3/2, would be 3/2 x to the 1/2. And of course, the negative that's here would continue there. So here's the derivative. I'm going to rewrite it with a square root, so it's a little bit easier to understand what's going on. So the derivative, if we draw a sign diagram for it, would have a 0 at 0. And of course, the domain for the original function, since there's a square root in it, there's no permitted values below 0. And above 0, all the values are going to be negative, right? Because if I put any number into the square root that's positive, it's going to be positive, and then I have a negative 3/2 multiplying. So basically, there is a stationary point at 0, and then so it's at that point there is it's flat, and then it's going to decrease as we go to the right. Okay, so that's the approximate shape of I. Down to 3. At what value of x does the quadratic function ax squared plus bx plus c, where a is not equal to 0, so it's just a quadratic in standard form, have a stationary point. Under what conditions is a stationary point? A local maximum or a local minimum? Okay, so if we have this function, we would find stationary points again by finding the derivative. And the derivative of ax squared plus bx plus c would just be a times 2x plus b, right? And plus c would just take the derivative plus c, it would be 0. So that would be 2ax plus b. In order to find the stationary points, we'd set it equal to 0. We would solve for x, so that would be 2ax equals negative b. X equals negative b over 2a, which should sound familiar. This is the x-coordinate of the axis of symmetry, or the vertex. Under what conditions is the stationary point a local maximum or a local minimum? Remember that a quadratic or a parabola is going to have a local minimum if it opens up. And it opens up if a is greater than 0, right? And if it opens down, a, which is less than 0, then it's a local maximum. Okay, so that is the answer to that question. Number 5. Here we have a cubic, and it says it has a local maximum of -4, and it tells us to find a. So they're asking us kind of backwards, right? So of course, we're just going to go forward with our normal procedure, which is if we want to find the stationary points of a function, we find the derivative of the function. So it's going to be 6x squared plus 2ax minus 24, and the derivative of 1 is 0, so we don't do anything there. We set it equal to 0. And then we're going to say, okay, so basically we find out that the stationary point is -4, okay? And it says what value of a would make x -4 and make this 0? So it's kind of a backwards problem where we already know what x is supposed to be. So let's go ahead and put -4 in for x, and then we'll find out what a is, because a will be the only unknown then. So 6 times -4 squared plus 2a times -4 minus 24 equals 0. So we have these huge numbers. We could divide everything by -4 and make it a little bit easier. So then it would be 6 divided by -4 plus 2a and then plus 6. Okay, that's nicer. Minus 24 plus 2a plus 6 equals 0. So I could combine the -4, -24, and 6. It would be -18 plus 2a equals 0. So 2a is equal to 18, and a is equal to 9. Okay. Number 7, last one. Consider f of x equals x natural log of x. For what values of x is f of x defined? So f of x is defined for the values that natural log of x is defined, right? X, it's not choosy. You can put any number in there. Natural log of x, of course, only exists for numbers greater than 0. So this function only exists for numbers greater than 0. Show that the global minimum value of f of x is -1 over e. Okay, so first we need to find the stationary points. After we find the stationary points, we would need to test the endpoints to make sure what the global minimum is. Okay, so let's find the derivative of this function. We're going to have to use product rule. This would be u and this would be v. U dash is going to be 1. V dash is going to be 1 over x. So we're going to multiply. X times v dash, and we're going to multiply v times u dash, and that'll be our product rule implementation. So x times 1 over x plus natural log of x times 1. So basically that's 1 plus natural log of x. So that is our derivative function, 1 plus natural log of x. So are there any stationary points here? Let's see. Stationary points would exist if this equation is true. Natural log of x is -1. When is natural log of x equal to -1? If we do snail rule, we would find out that e to the negative 1 is equal to x. Okay. So this would be a stationary point, right? Okay. X equals e to the negative 1 would be the stationary point. How do we show that this would be a minimum or a maximum? So let's mark e to the negative 1 on a sign diagram. And if we put a very big positive number here, of course this would be a big positive number. If we put a very small number in here, less than e to the negative 1, for example, then natural log of x would be a negative number that is even more negative than negative 1, which would make this whole thing negative. So here is our sign diagram for the f dash function. Now, of course, this function does not exist for x is less than x is less than or equal to 0, right? So like at 0, there's an asymptote, and then nothing over here. So how do we know that negative 1 over e is a minimum? Because if you look at the sign diagram, you can see that the derivative is saying function goes down here, flattens out here, and goes up. So we know that e to the negative 1 is a local minimum, at least, right? It's at least a local minimum. How do we know it's a global minimum? Well, in order to figure out if there are any minimum points that are lower than the local minimum, all we need to do is check the endpoint. So we would just check here, and there are no endpoints on the right side because it goes on forever. And apparently from the sketch, we can see that the left side endpoint is going to be at a higher point than this region here because of the slope here. So yes, global minimum at negative 1 over e.